Let's start by talking about the enthalpies of reaction. This will be a bit of a refresher from what you've seen in general chemistry before we actually start looking at the organic molecules themselves. But just to kind of generalize this process, you may recall your typical combustion reactions of organic molecules, hydrocarbons like this alkyne over here on the left side, reacting with dioxygen, forming carbon dioxide and water. And this gives you a delta H of reaction that tends to be exothermic. One way of finding out that value is by using bond dissociation enthalpies. And the formula that you use for this is the sum of the bonds broken minus the sum of the bonds formed. Bonds broken being represented by the bonds of the reactants, and the bonds formed being represented by the bonds of the products. At the end, we divide this by the moles of the substance in question, which is usually the organic molecule. So provided you have the bond dissociation enthalpies of those type of bonds handy, then you could utilize this equation to find out the enthalpy of the reaction. And generally speaking, the process is simply an account of how many type of bonds you have in the molecule times the number of molecules that are present in the reaction. So looking at the carbon-carbon triple bond, there's only one carbon-carbon triple bond in this molecule, but there's two molecules, so we multiply 1 by 2. There is, however, two carbon-hydrogen bonds in this organic molecule, and there is two molecules of that kind, so you multiply 2 by 2. You have 5 oxygen-oxygen double bonds present. You have 2 carbon-oxygen double bonds in the product, and you have 4 of those CO2 molecules present, so you multiply 4 by 2. You have 2 OH bonds in water, and you have 2 waters present, so you multiply 2 by 2. And notice that I'm keeping the reactants together and the products together. So what you basically do is you multiply the number of bonds in the molecule by the number of molecules to get the following values over here. You enter the actual bond dissociation enthalpies for each type of bond. You carry out the multiplications. You add the values together in each one of the brackets. And then you carry the subtraction of the sum of reactants minus sum of products, or bonds broken minus bonds formed, divided by the moles that you see for the organic reactant, which in this case is 2. This tells us that the reaction is indeed exothermic by a value of negative 828 kilojoules per mole. Alright, so we're going to use that premise to explain what happens in the course of a radical reaction. And there's 3 steps to the radical mechanism. There's the initiation step, where the radical gets created. There's the propagation step, whereby a radical is introduced and leads to the formation of a different radical. And then there's a termination step, where the radicals come together and they form a regular bond, thus terminating the cycle. So we're going to start with methane, CH3, methyl in other words. And what we're looking for is the substitution of that carbon-hydrogen bond into a carbon-halogen bond, right? So carbon X. And the first thing that is going to happen here in the initiation step is that the weakest bond of the reactants is the one that has to break into the radicals. And between a carbon-hydrogen bond and a halogen-halogen bond, we've already established that because of the size of hydrogen and the length of this bond, we know that the carbon-hydrogen bond is a lot stronger than the halogen-halogen bond. So we expect the halogen-halogen bond to be the molecule that creates the radicals in the initiation step. So you provide the energy to that dihalogen, break it apart, and you end up forming your monatomic elemental radicals. This is it. This is the initiation step. There's nothing else to it. You start with no radicals and you end up with only radicals. That's what the initiation step is all about. Once the radicals get formed, this is when the actual reaction takes place, because you form the radical with the molecules that have the weakest bonds. And that could even be peroxide, by the way. We did talk about peroxide in earlier videos and how it does have a relatively weak bond, even weaker than the chlorine-chlorine bond. So what happens in the propagation is that you start the process. You now let your radical interact with your organic substrate. And what ends up happening is that the radical that has been freshly formed is lacking an electron. And so what it does to complete that pair and form that electron pair is to basically steal an electron from one of the bonds in this molecule. But it doesn't just steal the electron. It steals the electron along with the external atom bound to that molecule. So in the process, you end up forming an HX bond, but you create a new radical. You create an organic radical, in this case, the methyl radical. And this is the first step in the propagation step. In the second step, the freshly organic radical that has been formed reacts with another equivalent of XX. And in this case, much like we saw before, the radical is going to steal an electron from this XX bond, but it's going to do so by bringing the element X along for the right. So you're going to form a new carbon X bond, and at the same time, you will form an X radical. So notice that in each one of these events, we start with a radical and we form a new radical. Start with a radical, form a new radical. That's what the whole basis of the propagation step is. But the other thing to notice too is that you started with X dot in this process, and by the end of the propagation, the second propagation step, you have reformed X2. This is in essence what qualifies any substance as being a catalyst. And this is in essence also the reason why you have to be careful with radicals, because once they get formed, they engage themselves in a cycle that is catalytic. So if you accidentally introduce too many radicals in a reaction and the reaction happens to be exothermic, you could end up in a runaway reaction that leads to so much heat formation that you end up producing basically a vessel of high pressure that could potentially explode. So you got to be careful with radicals. The second thing that I want to point out is that if you look at the propagation step number 1 and the propagation step number 2 and you add these two steps together, notice that, as I pointed out, the X radical cancels out because we started with that and then we ended up reforming it. But also the intermediate organic radical cancels out. We have it appearing once on the product of the first propagation step, but then it becomes a reactant of the second propagation step. So overall, the only things left over are the reactants and products of the overall reaction that we have up here. So the sum of the propagation steps is equal to the reaction going on. All right, so now let's take a look at the actual energies of these processes, and we're actually going to start from the end because why not? Let's go backwards. So let's first calculate the enthalpy of the full reaction, the one that we see down here. Okay, so we're going to go up to this slide, and the idea is that we have a table right here for the bond association of specific bonds. So here you actually have to be very careful not to pick any random carbon halogen bond or any random carbon hydrogen bond. You have to pay attention that it comes from a methyl group specifically in this case. So the reactants are still the bonds to be broken, the products are still the bonds to be formed. So as far as bonds to be broken, the CH bond will be broken and the XX bond will also be broken. So that is part of the first set of brackets. And the bonds that are forming are the carbon X bond and the HX bond, which are the products, right? And we're going to subtract the bonds of the reactants with the bonds of the products. Bonds broken minus bonds formed. So in the case where X is fluorine, notice that the FF bond is 159, so we're going to have that input in there. Now the CH bond, that's going to be a constant in what I'm about to do. The CH bond, as you can see in the table, for methane is 435, so that's what we're having here. The CX bond that we're forming, in this case X being fluorine, is going to be methyl fluoride, which is 452, so we're going to input that in there. And HX, which is hydrogen fluoride, is 569, so that's the values that we have input in here. If you carry out the summation of the bonds broken, the summation of the bonds formed, and subtract them from each other, you're going to find out that the overall reaction gives off 427 kilojoules per mole. So fluorine is really a big player in this reaction, especially when you compare it to chlorine, because when you do the same analysis and introduce the values for chlorine and H chlorine bonds, those values are different than fluorine, and what ends up happening is that the overall enthalpy of the reaction is still exothermic, but it is less exothermic than it was with fluorine. The other thing too is that if you now move on to bromine, once again the XX bond dissociation enthalpy changes, so does the HX, and the overall enthalpy is now even lesser in terms of the negative value. So this is less exothermic than the previous two. And by the time you get to iodine and introduce the corresponding amounts for the XX bond and the HX bond, you have actually made it into an endothermic process. This is no longer yielding energy as the reaction goes from reactants to product. This actually needs energy to form product. So this is not a preferred situation. Okay, so we're going to input those values in here for the reaction. So we have the fluorine column, the chlorine column, the bromine column, and the iodine column. And what we're going to do is simply look at the individual steps. As we already know, the sum of the individual propagation steps is going to equal the overall reaction. But we're going to see what happens at each individual step, because some interesting things happen. So if you perform the same calculation, and notice here that for the first propagation step, the only bond that's broken is the CH bond. In the first propagation step, the only bond that's formed is the HX bond. So you will subtract the value of CH with the value of HX, and that will yield the values that you see here on this row. Likewise, if you look at the second propagation step, the only bond that's broken is the XX bond. The only bond that's formed is the CX bond. So you subtract the values for the XX bond with the value of the CX bond, and you will get the following values. Okay, so here's what I want to point out. Yes, if you add the two values together, you get the value of the overall reaction. But what's important to notice is that in the first propagation step, fluorine is the only element, at least with methyl, that yields an exothermic process in the first propagation step. All the other halogens are endothermic. Now, chlorine is, for all intents and purposes, pretty much neutral. That's very close to zero, so that's kind of neutral. But fluorine is exothermic for sure. Bromine and iodine, on the other hand, that's not looking good. And even though in the second process all of them are exothermic, the fact that the first process needs to happen first, right? If this doesn't happen first, you don't get the second process to occur. What this is telling you is that fluorine is going to go like big time. This reaction is going to take place. If you accidentally make too many fluorine radicals in your reaction, you can get a runaway reaction here for sure, because even in the first step, you're kind of screwed. You're getting already quite a bit of energy. And on the second step, you get even more energy. So yeah, you have a lot of energy with fluorine. So you have to be careful with that element. Chlorine, even though the first step is kind of neutral, the second step, if you can get some of it to go forward, in the second step you get more than enough to make up for the fact that this is neutral. So this reaction with chlorine is still doable. But bromine and iodine, not so much. The amount that you require, the enthalpy that you require to get the first step going is 69 kilojoules per mole. Even though the second step is negative 101 and the overall process is negative 32, you're only getting in the overall process 32 kilojoules of energy, which is not enough to pay the price of 69 kilojoules per mole. So this step with bromine is technically stalled. You're not really going to get much of it in this radical reaction. And iodine is even worse, because here not only is the first step highly endothermic, the overall step doesn't even produce heat. So here you're definitely done for. Iodine is not good. And what you're going to observe in the subsequent slides is that iodine, yeah, it's a disaster. You don't expect to make carbon-iodine bonds via radical reactions. They're just not going to happen. But let's move on forward in the series. Let's go from methyl to a primary carbon. ethyl pretty much. So if we have ethane right here and we want to do the same process, we have the same reactions. In this case, ethane reacts with the freshly formed halogen radical that abstracts a hydrogen atom to form HX and your freshly, introduced organic radical. That organic radical serves as the reactant in the second propagation process, which reacts with another molecule of X2 to produce your final organic halide molecule and reproduce your halogen radical. Now, one thing I didn't mention earlier, but it should be stated right now, is that the reason why the second step happens with a second equivalent of XX is because you are not actually forming a full molar equivalent of the radical when you undergo the initiation step. In the initiation step, you're at most making, even this will be an exaggeration, but you are at most making 1% of the radical out of X2. So what that means is that you still have that 99% X2 still present in the reaction. So the likelihood that this organic radical will see X2 in the mixture is very high. So this process is definitely a possibility, and a plausible possibility at that. Add the two processes together, the two propagations, you get the overall reaction. And if we perform the same calculation we did before, right, bonds broken minus bonds formed, consider that you're breaking the CH bond, the XX bond, and you're forming the CX bond and the HX bond, you find out something similar, that for fluorine, you get the most exothermic process. Chlorine, you get exothermic process, but to a lesser extent. Bromine, also to a lesser extent. And iodine, once more, it's endothermic. Now, if you look at the overall propagation steps, what you now find out is that if you use a primary carbon, chlorine is now yielding a exothermic process in the first step. So now fluorine and chlorine are definitely good to go with a primary carbon CH bond. And so these two elements will not require the addition of heat or anything like that to get started. The moment you have that radical present, this process is going to go forward. So you have to be careful with fluorine chlorine because it could be bad. And fluorine for sure. I mean, that is 4 times more heat produced than you get with chlorine. So you have to be absolutely careful with fluorine. But bromine is still endothermic in the first step. So is iodine. But the one thing you will notice is that bromine, the endothermic process compared to the overall process, it's almost neutral at this point. So you're kind of like breaking even. So it's not good enough to get the formation of product consistently to a high yield. And in fact, in this type of reactions with primary carbons, you seldomly see bromine engaging in the formation of that radical. So technically speaking, in this state, bromine and iodine are still no good. They don't get to form that organic halogen product. All right, so moving on to the isopropyl case, in other words, the secondary carbon. If you look at the values for the overall reaction, once again, fluorine is highly exothermic, followed by chlorine, but this time bromine is also exothermic, and iodine, breaks our hearts once again, fully endothermic. All right, comparing that to the individual processes, notice that, yes, fluorine and chlorine are negative even in the first propagation step. Bromine is still endothermic, but notice that the overall energy that you're getting from the full reaction is now 64 kilojoules of energy. That is more than the energy that you require in the first step. So if you get 1 molecule of your secondary alkane to react, by the end of this process, you're going to produce enough energy to continue the reaction on its own. So at that point, it becomes a reaction that doesn't need any more heat input from you. So bromine can definitely do something with secondary carbon. So this looks good, but look at iodine. This requires 98 kilojoules per mole in the first step. You're barely getting 27. In fact, you're not getting anything. You're you're providing 27 to it. So iodine is still terrible. It's not good. And even for tertiary, what you're about to see, iodine is gonna, it's gonna suck once more. We get the values for the tertiary halogenation of the organic molecule. And if we compare the the first propagation step and the second propagation step, what we find out is that fluorine and chlorine are still negative throughout. Bromine remains positive, but like in the previous case, the value of the first step is 15 kilojoules per mole, which is not too bad. You can actually access that even at room temperature. And by the time you finish the reaction, you get 4 times more energy out of that process. So you have more than enough energy to then pay off the price of the first step. So once this gets going, it will keep going throughout. So brominations of tertiary alkanes are definitely not only possible with bromine, but they are quite efficient as a result of this. But iodine, on the other hand, you have a high price to pay on the first step, and on the final step, you don't even get energy out of it. You have to put in energy. So the take-home message here is that iodine will never be used in a radical process to make carbon iodine bonds. There will be other reactions we're going to discuss in the future that will allow us to introduce iodine as a bond with carbon, but via radicals it's just not going to happen. And the second thing I want to point out too is that bromine is very selective as to which type of carbon it reacts with. It prefers the tertiary carbon, and to a lesser degree it will engage with the secondary carbon. On the other hand, chlorine is good with pretty much all of them. Methyl struggles a little bit but still gets it going. But any other type of carbon, chlorine is more than happy to engage with and carry out the process. So chlorine is going to be less selective than bromine, as we'll see in the future video. Okay, the last step of this process is the termination step. And the termination step is when two radicals meet each other and basically decide, okay, let's hook up, let's make this happen. And you end up forming that new covalent bond. That's the termination process. You start with only radicals and you end with no radicals, right? And this could also happen, by the way, not just with X and X, but it could happen with the organic radical and the X radical. It could even happen with two organic radicals, although these two steps right here are a little less likely to happen. But technically, if they do see each other, they do count as a termination step. The most common one is the first one that I introduced right here. So altogether, initiation, propagation, and termination accounts for the entire mechanism of the radical reaction. In the next video, we're going to talk about the overall reactivity of the CH bonds, and we're actually going to do some calculations. So I'll see you then.